Hello CS300 and welcome to my video on time complexity. So as you might already know, time complexity is how we as computer scientists measure how long our algorithm or our methods are running. So in Java Visualizer, I have a simple example of this where I have my variable n, which is initialized to 10, and I'm creating an array based on that number. So with time complexity, we really have to be paying attention to our input within our methods. That's the important part, like what we're doing with our input. So in this case, my input is that array of size n, which is 10. And so if we go down to this method input example, all we're doing with it is iterating through each element in that array one time. So if I put n as 10, then we can see that when we visualize this, then it's going to execute exactly 10 times, which makes perfect sense. But if I change that to be 20, then it's directly correlated and it's going to be running exactly 20 times. So as we double our number, the size of our array, the amount of times that this for loop has to execute is directly correlated, which means it's big O of n. What I mean by big O of n, if you're unfamiliar with that term, is I'm using big O notation to describe our time complexity. I'm going to hop on over to Eclipse to kind of clarify this idea a little bit more. So you can see that I have the same setup here. I want to show you what big O of n would actually look like. So it looks like this. Hopefully you're familiar with that by now. If not, then I would definitely read through the Xi books on it. There's actually some really helpful stuff on big O notation in general, as well as some other notations we might use, such as omega and theta. Two things that I will not be going over in this video because I think at a certain point it's kind of just memorization. If you have more questions on it, please feel free to Skype call me or go to any office hours in general. But yeah, I will not be going over this in my video. One really important thing with big O notation is that we drop constants. And so what I mean by constants are all these little things within here that kind of happen, but in the long run, they aren't really going to matter. So for example, this right here is going to take constant time to initialize this variable. So at the end of the day, we're like, okay, we don't really care. The important part is that we're iterating through each part of our array. That's our input that we're paying attention to. We're not paying attention to the fact that we're incrementing j every time we go through or anything like that. So if I had some constant attached, then really at the end of the day, this is just big O of n. It would be more than just one, but this is just one example. And even if I had another for loop, let's just copy. This right here would actually be dropped off too. So it would look like big O of n going through n times plus another n. And as this goes to infinity, then that's really just going to be big O of n. And when I say going to infinity, I want to be using this to kind of describe that. So you can see as we keep going on with our operations on this side, then there are certain time complexities that are going to end up being way worse than others. So big O of n square is, not very good. In fact, they label it as horrible, whereas O of n is not too bad, and constant time is going to be pretty much, the best. If you're curious, this is from bigocheatsheet.com. I'll be putting the link in the description. It's helpful to look at these different data structures and their time complexities for each of their different methods that they have. I always found this to be really helpful personally. So you may be wondering now if two different for loops would still just be big O of n, then how do you get something as bad as O of n squared? And the answer to that is, for one, nested for loops. That's kind of, I guess, the standard for an indicator that something is going to be big O of n squared. So we have two for loops inside of each other here. So typically, that would be a good indicator that it'd be big O of n squared. Except you may notice in this for loop that I'm actually only going up to 10. It's not dependent upon the input here. So if I had just a for loop by itself, and it just went up to 10 here, this would never change. No matter how big my array gets, this will be constantly going only up to 10. And so right here, this for loop is actually just adding on O of n, or sorry, not O of n, O of 1. So this is constant time. So if I have a nested for loop here, don't let that trick you into thinking, oh, this is always going to be O of n squared. This right here, this for loop, inner for loop, is going to be constant. And so really at the end of the day, this is just O of n plus, O of 1 time, which would just be O of n. So really, overall, this method is just O of n. If I did change it to be dependent on the array length, then that would be O of n times n, which would just be O of n squared. I think O of n squared can be kind of confusing, so I'm going to go back to Java Visualizer to kind of show what's going on here. So I've got my nested for loop now, and to put it into words, I guess, before I execute it, basically this is going to go through every single element in the array, and for each of those elements, it's going to go through every single element in the array. So you can see how that would be pretty time consuming. If that doesn't quite make sense, then hopefully visually it will help you out. It might take a while because it's big. Yeah, so it says exceeded max visualizer time limit. So it's pretty mad about this. Okay, so we go into our outer for loop and we go into our first element. Okay, and then for that first element right here, it's going to go through and it's going to print out hello for as many times, as many elements is in the array, which is kind of a lot because n was 20. And now we're finally in that second element and we've already printed it out 20 times that first one, and now we have to do it 20 more times. So it will essentially do it 20 times for each of the 20 elements in the array. So that would be about 400 times in this case, or 20 squared, which is why this would be big O of n squared. If I put in 40, it would be 40 squared, which is a much larger number. And so it's increasing drastically, which brings us back to our chart here. It's increasing in a very horrible way. It's increasing incredibly fast. Which is why if I ended up adding on another for loop outside of this, at the end of the day, that for loop would be, let's just say I added it, a for loop here would be insignificant. It wouldn't matter. I mean, this would just be big O of n. So overall, this method would just be O of n squared plus n. And the n, just at the end of the day, it just doesn't matter in comparison. It's growing way, way faster because of that O of n squared, which is why we tend to just drop those more insignificant parts. It's important as computer scientists to learn about this stuff because really we want to get the best time complexity we possibly can. To put it into a real-world example, I guess, let's pretend we're in CS300 in a classroom, and we want to find somebody who has the same birthday as us. So one horrible way we can do it is ask every single person in the room and have every single person ask every single person in the room, which of course would be O of n squared. A way easier way of doing that is just to ask every single person ourselves. So if we just ask every single person ourselves, eventually we'll find that person. We don't have to have every other person then ask every other person. That wouldn't really make sense. It'd be way faster to do it that way. Even better, we could just put the birthday we're trying to find on the board, and assuming everybody cooperates properly, we just have them raise their hand if they have that birthday, and we pretty much would find that person instantly. So ignoring factors that could go wrong there, that would be constant time. So a couple good takeaways from this video. So time complexity is something that is typically measured with big O notation. And again, there is omega and theta, which is important to learn about. I'm not going over it. And basically, big O notation is what we use because it deals with the worst case scenario. There are some cases where our methods could end a little bit earlier, but they still also could iterate through every single element, or in the case of the nested for loop, iterate through every single element, and then every single element for each of those elements. And that would be the worst case. So we do big O notation as programmers because that is just good practice, because that is, what it could end up to be. So big O notation means you'll drop off any constants, or again, anything that is insignificant compared to the biggest row. So if I had O of n cubed plus n, then of course this would just, at the end of the day, be O of n cubed. But if I had O of n cubed times n, which would be kind of a nested for loop situation, or a really nested for loop situation, then that would actually be O of n cubed. If that was kind of confusing for you, I recommend going over the section in Zybooks 14.1. Looks like this or this. So this goes through kind of the rules for knowing when you want to drop something. And these examples are pretty helpful. And lastly, that some time complexities are better than others, like O of 1 is better than n log n, and it's much better than n squared. I really, again, want to emphasize that sometimes for loops can be constant, and it's really important that you pay attention to that. If you're ever in a method going to be doing the same amount of work, so let's say we're going through a linked list or something, and we're always accessing the fourth element every single time, no matter how big our linked list gets, it's always going to be the fourth element, so even that would be constant. I think it's really important to go through a bunch of examples like that. There's a great section right here in your Zybooks that goes through a couple different time complexities and examples for that. I definitely recommend going through this section in depth, and if anything doesn't make sense, definitely clarify it with one of us. You can have a Skype session with me or go in and talk to Andy or your TA. Definitely you want to get this stuff down. Time complexity is a very important programming concept. That's all for today. Good luck with your next program.